paper. Published in Field Trip Guidebook for the Friends of the Pleistocene 2004. You can get it on the Pacific Cell website. I want to point out some things, so I'm going to quickly just put these things down so you can see. The basic topic today is what happens to sea cliffs when waves attack at their base. So some of the terminology I'll be referring to is the marine terrace, which is interpreted as an uplifted abrasion surface. An abrasion surface or platform forms as the sea cliff is retreating by waves attacking and grinding away at this bedrock. So these splashes are intended to be bedrock. These are profiles. So we're looking on edge at the sea cliff. Typically, marine terraces have sediments like beach type deposits on top of them, having come up out of the ocean by uplift over time with the, conflating factor of sea level rise and fall with glaciation. This shoreline angle is a generalized term. The term wave cut is very ambiguous. We'll talk more about what that can be interpreted as. And the types of features that are more commonly found in textbooks would be the shoreline angle, an abrasion notch at the base of the cliff that undermines the rocks, leading to landslides and rock falls, the typical ways that the sea cliff fails, the rock in the sea cliff fails. We're not going to get into that. We're really just going to be talking about what's happening down here in the submarine domain primarily. But you're going to be introduced to some new features. I'm going to talk about an excavation bench and abrasion ramp that sit above the abrasion platform and top out just about where beaches would normally form. A beach here, typically in Southern California, during summer, we might see the sand accumulate up, a wide berm build out, the beach face where the waves are swashing back and forth, up and down. And then offshore, we might have a trough and bar of sand. And a lot of this beach during the winters, there'll be so much reflected energy off the sea cliff, big heavy waves coming in. A lot of this sand will literally shift offshore and store in a berm if not being washed into deeper water. So one thing I want you to think about is that the top of the beach is typically somewhere near the high tide wetting line. And that's going to come in right in about the top of this excavation bench, the top of that notch, and then somewhere in here, that's maybe something like, mean high tide. And then somewhere down below that in the low tide area is where we're going to find abrasion platforms exposed when the sand is washed away. Another thing is the influence of the shoreline coast, the shape of the shoreline on wave energy. Where the shoreline juts out and forms a headland or a salient, something sticking out, typically waves are reacting to the bottom rock and converging for the headline, concentrating energy there. And in coves, the waves tend to spread out, wave refracting bends that wave energy out and reduces that energy concentration in a cove. So you'll typically see beaches here, no beaches here. Now, the specific topic of concern today is something called a shore bench by Douglas Johnson. And he's a geomorphologist like myself, which is that crossover discipline between geology and geography and physical sciences. And back in an article in 33, he studied this topic for quite a while, but he published it in the Geological Society of America Bulletin. And he mentioned these shore platforms cut in above high tide. This is the only figure in a 30-something page article. If you have time to read this article, you'll find it joyous. It's about scientific inquiry. And he's the one who really kind of inculcates the whole scientific method. And you'll find references to classic works like T.C. Chamberlain's method of multiple working hypothesis and the origin of hypotheses by famous G.K. Gilbert, referred to in his work here. Worth the read, long read, worth every page. Is what he refers to throughout is his paper is the origin of these shore platforms, and they were controversial even back in the 1880s when J.D. Dana first published his Manual of Geology. So we're going to be looking at differentiating the effects of abrasion and excavation. This is Point Mugu. And we're going to look at features of the sea cliff primarily. There will be human-made structures there for reference. And of course, human-made structures are great references for rates of change because they more or less stay still, stay put. But that's not always the case. So we've talked a little bit about a sea cliff. I've introduced the notion of wave abrasion. The abrasion platform is being worn down the bedrock under the waves by sediment moving back and forth. And that platform is extended landward as the sea cliff retreats. The notch here is kind of the classic feature that is always referred to in textbooks. I'm adding another feature here I'm calling the abrasion ramp that I want you to learn to identify. And then we'll talk about the significance of that very soon. Just a refresher again, abrasion is occurring below high tide, and evidence of what's happening there is in the rocks themselves. They're darkened by frequent wetting, and they get smoothed by that abrasion. So angular things get rounded. And again, the platform, the notch, and the ramp, and I'm now, and this is only because I've been re-studying this recently, beginning to believe that the ramp, even though it is in the zone of abrasion, is evidence of wave quarrying and excavation at a higher level on the sea cliff. And I'll hopefully explain that to you in due time. So what is this wave excavation I'm talking about? In old literature, they'll refer to it as quarry, where the waves are slamming into a sea cliff or surface, injecting water at high pressure, blasting away weakened loose pieces of rocks that have been weathering in that zone above high tide, the part that maybe gets wave splashed, but then it dries out just about every day. And what happens is that weakened rock will excavate out on a relatively almost horizontal level. So what are we going to look for? We're going to look for these benches that are cut into the sea cliff themselves. And then if those get isolated and separated, the sea cliff retreats faster than the abrasion down below the bench. They might actually become isolated as a terrace. And we'll see evidence of that in my interpretation of, I'm going to cut to the chase, of Campus Point at UC Santa Barbara, is that this is a large excavation terrace that was formed in place, rather than what many geologists have been frequently referring to it as an uplifted abrasion platform. So we'll talk about the evidence that makes the distinction between those. And I'll be referring to 4 different locations throughout this, and I'm going to identify them real quickly. Down in Solana Beach, where we've got Eocene sandstone, it's 50 to 50 million years old. Point Furman, where we've got some Miocene sandstones and shales. Also Point Mugu, Miocene sandstones and shales. And then Campus Point out here near the campus of UC Santa Barbara, where we have a younger sequence of rock, the Sisquoc Shale, in which that Pliocene Sisquoc Shale is silty and weakened and young. So it arose rather fast, and excavation benches and terraces form exceptionally well in these materials, these softer materials. And one of the reasons is, of course, they've got a lot of clay in them as well as the silt. And when they wet and dry, they undergo some expansion and contraction. Folded rock is already typically fractured, so it's got some inherent pathways for water and salts and other things to accumulate. So back to Point Mugu. You can see here in a sequence of photos that we're losing some pieces of human-made structure. The road that once went around, I think it went around in the early 30s around Point Mugu. And then they cut a big pass inland and abandoned it in the 40s. So it didn't have even maybe 10 years of service before they gave up on trying to maintain that road. So other thing to note is that a lot of times the sea cliff is self-same. It looks similar. And so if you don't have features such as these to key to, it's hard to sort of interpret change without something to reference that's, you know, that's not the same as the materials that are there, the rocks that are gonna be eroded. So looking to the west, Point Mugu, that's the pass right there where the road goes through now. It used to go around here. We're looking from Sycamore Cove Beach. That's the beach right in this little gap right here. So let me see if I can advance this forward. And we're looking through a little gap in a volcanic dike that is cut through the rocks and into the surf zone. And the reason I'm showing you this particular view is it's not the material we're gonna see mostly. But we've got man-made stuff that's been added, but it's not staying put, it's mobile. And some of that has drifted down into the beach zone, if you will. And what I'm gonna emphasize are these two domains of weathering. One that's below that line roughly, and that's the zone of submarine weathering. And it's really characterized by the rounded and smooth and darkened materials of the beach. Whereas above that, we're getting subaerial weathering. And then occasional wave attack in this domain that takes large chunks of angular sandstone riprap like this and jostles it around and eventually puts it down into the beach domain, where it just becomes another element of the abrasive submarine weathering. Now, we're backing over to Point Fermin, where I love to lead field trips, one of my favorite places. And Point Fermin juts almost kind of due south. You take Gaffney all the way down, you'll hit Point Fermin Park. What you can see in this photo are some distinct beds here of the Monterey Shale. This is the Altamira member of the Monterey Formation. And then some larger, thicker sandstones that hold up a steeper cliff face here. Where the shale comes in and meets the sandstone is right about here. So these are south dipping strata. Their layers are tilted down to the south. The layers that jut out here are a little more abrasion resistant. So that means the rocks in between them are eroding down faster, and these ones stick up because maybe there's a little more cement in them. They're a little harder. There are ways of testing that hardness. This is also in a cove, so it has a little less energy. And what we can see is that the cliff here is vegetated and it's staying relatively stable. And a beach is there to protect the base of the cliff from wave attack. And the berm on the beach is where driftwood and such things accumulate. The beach face is that swash zone. But notice that your beach just peters out over here. Just about where we go from a stable sea cliff to this steeper, maybe, you know, constantly challenged by wave activity. There's also some debris that's come off of that face and accumulated right in here. And then as we move along, we've got large boulders and things all the way up till about here. And then we have this platform out here. So I'm trying to make sure, integrity-wise, to point the things out that I see before I give you an interpretation and make sure I make a distinction between my interpretation. My interpretation is, of course, that we have less energy in here and more energy from waves breaking, and even higher energy at the point itself. And the key to understanding that is what's there. Small material that makes up the beach here, large blocks of chunks of rock here, and then so much energy that when the waves break here, nothing can stay there, it gets swept away. So we're going to take a little closer look and see if that holds. But first, I want to let you see what it kind of looks like when we've got higher wave energy hitting and washing over some of these surfaces. So this is a little more of a close-up there at Point Fermin. Now, if we go out onto the point and we get on that platform where there is no rock material accumulated, and look back, we can see a darkened zone in here, a lighter zone above. I want you to also keep track of this big patch of white here, which is mostly salts efflorescing from the park above being watered and the water percolating down, maybe hitting some of these impermeable shale layers and then moving out to the face and then dripping down the face. And as they evaporate, the salts stain that surface. Notice again that there's a lot of boulders and things in here, the large angular material. The more angular, the more likely it has been to be more recently introduced. But notice again this dark below, light above on that angular material and on the rounded material down here. Some people in there for scale. I love to take my students here because if they can scramble out this far, they can see the tidal zone in a vertical profile, which is kind of great instead of having to kind of search around for it horizontally. So it's kind of concentrated there and it's a pretty steep environment. Now let's look in at these materials, this jumble of stuff that's coming down from above. There's some vegetation that came from the very top attached to a block that's landed in here. It's kind of canted and leaning over. The angular material that has yet to be sort of hit by the waves. But some of the material in here is rounded. It's clear evidence that the waves come up and move that material, or carrying sand and moving that about has abraded these materials. There's something else to look for in response to wave energy, and that is that these rocks get tumbled back and forth until they kind of lap one on top of another. They do what the English refer to as shingle. Sometimes you see that in little cobbles and things, but in here we're seeing a little bit of, it's not really strong here, but a little bit of this orientation dipping toward the water. And what they do is they armor each other and they make themselves less likely to move. The waves onrush and just kind of flow over them. But in the most extreme events, there's so much energy washing up, hits the cliff, comes back, and those things can get flipped and move it again. So nothing's stable in this environment. But bigger stuff stays closer toward that bench, and the finer stuff does get kind of swept in toward the beach over time, and everything's kind of wearing down in time. Now we're heading way south. We're going to look at something less complicated. It's horizontal layer cake strata. The Eocene sandstone, the Torrey sandstone here is coming in here. Above, here's actually from here to here. Above that, where it goes from steep to laid back, this is all Pleistocene sediments, mostly beach sediments. And that stuff is weathering away, fairly easily. Down here, we've got a nice notch. But notice the beach here. The beach face comes up to here where we start to get material accumulated, like big wads of help me out. Yeah, I was gonna say kelp, but that's the same thing. And you've got a berm right here of these cobble materials. When I first saw beach change dramatically in the winter of '81, I was surfing just north of there in Leucadia. And a big white beach disappeared, and overnight cobbles just piled up against the base of the sea cliff. It's like night and day, and it's an extraordinary thing to witness. And I've been interested in it since then, but I didn't get really attached to studying it until about 1995 when I was a graduate student at UC Santa Barbara. We're going to take a closer look at that notch. That abrasion notch here, it has a height that correlates more or less with the top of the beach berm. This sandstone is pretty hard, it's pretty old. In Santa Barbara, where there are cobbles, and then they get washed away, you can see evidence that the cobbles have beaten against the rock because it leaves little dents in the shale. I didn't see that, somebody else pointed that out to me recently. So there's so much to be discovered in this environment that anybody who takes an interest in it is going to discover more that has yet to be revealed or interpreted. But one of the things we know is because people love to live near the ocean, that this will always be a place where people want to build homes and things. And this relentless erosion from the waves attacking is unstoppable. You can slow it down, but you can't stop it. So people build seawalls to try to protect their homes and nowadays they try to dress them up so that they look very much like the original material. So they put the concrete in there. They try to give it some other added features to prevent some of the typical problems with it, but seawalls are designed to slow that retreat of the sea cliff, to keep the sea cliff stationary. But ultimately, they wind up reflecting wave energy, especially at high tide, especially when there are big storm waves. And then that reflected energy strips the beach. So this is especially common in the winter. When in some cases, maybe the cobbles can't even stick around. Again, if what's happening is, even though the sea cliff retreat is being retarded, it's prevented from moving back, the abrasion platform keeps going down. And eventually the waves come in with more force because the water's deeper, they're unimpeded. So they're gonna come in and they're gonna slam these things. They can retain groundwater, they can actually maybe even lead to something like a deep-seated landslide if that is not attended to. And ultimately, because they prevent not only the sea cliff base from eroding back, but also they kind of trap some of the material that's naturally moving from above onto the beach. So they reduce the sediment supply. You know, a lot of our sediment beaches are reduced in sediment supply because we have so many dams. And so a lot of the beaches, even though they can get wider in the summer, they maybe could get even wider if they had a plentiful supply of sand, if a lot of these rivers didn't have dams on them. So let's look a little bit further along where a new, this is not new, this is 20 years old. They were building this back in 2005. There's that sandstone, there's that sediment on top. There's all the rebar that they're staging out. This isn't where this is all, there's like 3 sheets of it here. They're gonna move it out, and then eventually they're gonna, pour the concrete in here. They have all these tubes here that they're gonna aim out to help promote drainage. But here's the problem. See down here, there's a little seawall that was installed to slow that relentless abrasion. And there's a big seawall over here, a little older. How far down does this seawall need to go to prevent that erosion? Eventually, any seawall is going to get undermined. Unless you go super, super deep, but eventually, in due time, maybe a lot longer, it will ultimately get undermined. So what do you see in this picture? Anybody?
Is that a notch on the left?
Sure, so this is a piece of concrete that was once a seawall, like we saw in that previous slide. Placed down low at the base of the cliff to prevent abrasion, filling in the notch.
But it eroded behind it.
But not only is it being eroded from underneath, but yeah, up and behind. And we start to see, as this seawall has been abraded down below, we get up to a point where it still has that nice form, that edge, right, up here. And we start to see little things poking out of the notch up above. It starts to get into that zone of what I would call sort of the light and rough above, and then that dark and smooth below. And an interesting thing where the algae is showing up here. Well, as far as I can tell, the wetting gets up as high as here. But the algae is only showing up here. So it's got enough water to grow. But down here, what's happening, you think? That's being abraded away, right? It's being attacked by all the sand and gravel. So so we're gonna see this repeated, this sort of sequence. Yes, right.
It could also be that that's intertidal zonation vertically. That
No,
it just likes that right amount of exposure and water to
Right,
algae.
that's a good question about that. Perfect example of maintaining integrity in an investigation is not to dismiss a hypothesis. Because it could be exactly what you are biased against. Right? You don't wanna just throw out any possibility out of hand. You have to think through and analyze at every step of your investigation. And think of like, well, what evidence would it take to convince me that algae could live down here? In this lower zone. I would have to find a protected area that wasn't getting the abrasion. To see if that were the case. To dismiss that, right? Notion. I would have to analyze it and come up with an idea, right? Of how to challenge that opinion or hypothesis. So this is about keeping integrity involved, is again, don't throw anything out until you devise some means of definitively testing, or maybe not even definitively, maybe just. You're just testing out a possibility. You have to approach things with. You know, what do they say, the grain of salt, you've got to take it all with a grain of salt, but you've also got to take it with an open mind. Because the more we put on the blinders and more certain we are about an interpretation, the more likely we are to miss other things there are to see. And believe me, I've seen more from these photos than I've ever seen before, because I spent so much time kind of looking through them now and scratching my head again, certain that I knew what was going on. And now I'm also finding areas where I'm still scratching my head and happy to be engaged in the inquiry of science. So no matter what you're doing at the bottom, there's still sea cliff above. And that rock and material is coming down. In places where it's unprotected by a seawall, or maybe even when the seawall itself gets undermined and collapses and brings a whole lot of it material with it. And the people who are living in these locations are maybe more concerned about the building of the seawall when they should be more concerned about their own foundations and what's holding them in place where they are and how to control the surface waters. It's really an important element of sea cliff wearing is what's happening at the top, and sources of water. Irrigation and such things can lead to some serious problems. Maybe even a water pipe or something that shouldn't, maybe gets pulled out and, the sprinklers go up at night and it's just jetting water out into the, to the side of the hill. So now, all of this is leading to here. All of what I've kind of set up for conversation and inquiry. Campus Point has a unique structure out here that I have an interpretation of. To bring you there, I'm gonna kind of take you on a little trip here from Fish Rock all the way out here. It's a little under a mile. And we're gonna look at some features. This green line right here represents the boundary between Monterey Shale, which is Miocene and typically has some well cemented layers like the Altamira we saw at Point Fermat. And then this is a Sisquoc. And then there's a fold structure. Everything's dipping to the south, north to the top here, dipping to the south. Until you cross over this lagoon and you see Santa Barbara, and then the rocks start to dip to the north. So there's kind of a U-shaped fold in here. And right near Campus Point, we can see evidence of the abrasion platform with a thin blanket of sand here at the base of a sea cliff that's covered with riprap to protect it so it doesn't erode away. This little guy here, well, he's a big guy. He's 25 inches at the withers. That's Mojo Hound. God rest his soul. And this is that rock, that bedrock. I had another picture I wanted to show you with the little FOLAD clam borings. I didn't get a chance to put it in here. But the sediment moving back and forth in the swash zone from the waves running up and running back is wearing down this weak shale very fast, so fast that some of these little clams that live and bore into the rock can barely keep up. And if they can keep up, they can bore deeper and they can grow bigger. And they have kind of a fluted, frilly structure on their base that it's kind of like a rasp. And you can imagine that they have something pushing up, but they've got to kind of wiggle their body around to grind their way into the rock. And when you see them in the deeper water. Where the waves, where the beach materials are not nearly as concentrated, they can get pretty big. And on some of these marine platforms, the uplifted terraces, you can see some that are pretty deeply embedded and very large fossils, if you will. So a notch here. Out where we can see the materials, the tools that the waves are using. Is developing on some of the features in the offshore zone. What you're not gonna see much of for the rest of this is more of these notches. I'll show you where they kind of are, barely. But what we're gonna see is a very different modality of sea cliff retreat than we saw down in Solana Beach. And this process I refer to as wave excavation, and in old literature, we refer to as wave quarry. Is literally that digging away, the waves just pounding and tearing away at the weakened weathered material above that wetting line. The benches are gonna form at the base of the cliff, these terraces that I've talked about. When those elements, those benches get detached or separated and the sea cliff retreats without them. That's my interpretation. Now. Here is a typical sea cliff on the east beach of UC Santa Barbara campus. It's got a steep upper section, and at the foot, it kind of ramps down before you hit the abrasion surface down here. This little guy is Jackson. He's about 10 inches at the withers. Less than half the height of Mojo. And he's a real goer. He loves to be on the beach. Notice the dark and the light. If you get up close, you'll see that the dark is smoother, more rounded, especially as you get lower. And as you get higher, it's more angular. There's some other features going to show up here in a minute, but I'm going to take you, this is a stretch of beach below Lagoon Road. We're going to go back to the north end and look at the Monterey Shale. That previous one was in Sisquoc. In the Monterey Shale, we've got some very distinct beds that stick out from the sea cliff and also extend down into the abrasion domain. And you can see that dark transitioning into light. This tends to be smooth, this tends to be rough. It's very kind of, obvious thing. In one storm, this shelf was created by the erosion of this rock. So waves were held back from abrading by this very abrasion resistant layer. And then one storm took not only that layer away, but several other layers beneath it and left a bunch of hanging rock here. Moved it out and quarried or excavated out and extended this bench. Now, this area over here was probably also a bench in the past, and when the sea cliff was here. And so when it moved to here, we've got a new quarried surface. Everything else is in the domain of abrasion now. And this too will eventually succumb to abrasion. Eventually. Let's see what it looks like 30 years later. This, I believe, is the same layer right in here. But as the sea cliff is retreated, because the angle of the strata coming in, this has migrated to the west. So this bench has literally extended westward. And the parts that were unabraded, or at least not completely abraded away, have disappeared. But this layer is sort of holding up and generating impeding the subsequent abrasion of this material. During huge storms, you can probably imagine the possibility of sediment just getting stirred up, large material and small material. Did you have a question?
No, it's difficult because the promontory faces south. And so I'm sort of a little, my dorm room, I watched the sunrise and the sunset there. It was very confusing.
Yeah, right, so this is a view to the west. These strata are steeply dipping to the south. In this view, again, the stripe of the strata is more or less to the west. The light and rough and the dark and smooth transition is in here. And it kind of correlates with where our beach materials are topped out over here. Let's look at some more interpretation and perhaps evidence. But what's going to set up the possibility of a bench forming? First of all, you've got to retard that abrasion. If the abrasion keeps up at the same pace as excavation, then you just have a sea cliff. But if the abrasion is held back and the upper part retreats, then you can get a bench. That's the simplest way to kind of look at this. So you need some abrasion resistance below that wetting line. You need some weakening and weathering of the material above that wetting lines to make it susceptible to excavation. And then the waves have to get there to do their work. So either a thin, narrow beach or really big waves attacking and coming in full force to not only strip away the beach, but attack those rocks and strip. Yes, sir.
What's the difference between where the sea cliff is being raised and where it's being excavated?
Okay, let's look. Abrasion is really only effective in this wetted zone down here, where the waves are repeatedly washing material back and forth along and continuing to smooth this rock in here. So abrasion is in this submarine domain. It dominates here. Excavation is occurring right more or less at the top of that zone. So we put a line in here to kind of connect the dots. So abrasion below is dominant below. Excavation is a possibility above. Isn't necessarily gonna happen. But it's a possibility when waves are, storm waves are, level is attacked, so high tide maybe, and big storms. Will have the ability to raise the wave attack higher. But it's gonna be intermittent. Down here, waves are repeatedly abrading away and smoothing and darkening these rocks. Up here intermittently. Hitting with, big force. So I'm gonna back up one and just want to tell you, we're gonna look at this bench right here. This has been here for a long time. And it's not the same bench here in 2025 that it was in 1995 when I first looked at it, but it's in the same location-ish. We'll also see through a sequence of photos that the stairway here has changed configuration because it's gotten undermined. A lot of beach accesses do these at sea cliff domains. But here is the parking lot for accessing this stairway is right above in campus. And I want you to look at just a few things that you can see here. The layering of the strata dipping to the south, so we're looking to the west. The boundary between the sandy terrace deposits above and the shaly bedrock below, right in here, a little hard to distinguish. A big patch of broken rock that has, I interpret it as tumbled down and accumulated as talus on the sandy beach here. So now, any questions about this before I move on? You go one step further. Here's 3 photos, 95 and then 2 in 2025, just earlier this year. So you can see a similar shape. But notice again, you've got the dark and smooth, a little bit of algae, some salts maybe hanging up right here at the wetting line. And then goes right into this weathered bedrock. Notice the salt domain's much higher here. Well, I don't know what's going on there. And then just, 7 months after this, notice the beach covers up. All that you can see that's dark is covered by the sandy beaches built out. So I'm pretty sure that this wetting line really is controlled by high tide. That's always been its natural interpretation. But the fact that the beach accumulates up there also means that when the beach gets wetted, it's gonna retain that water and keep it in contact for a longer period than just the water washing up and then during low tide washing away. So maybe summer beaches have an important role in sort of maintaining this boundary. So that when the rock does excavate away, there is that boundary sort of still exists, maybe deep into the rock. So here's a profile from 2013. Here's another one with Jackson from 2025. And then just recently, I looked at these two sequential photos from 2013. And I'm looking at this box of concrete down here, which is the bottom of the stairway as a reference. And I was able to kind of scale them similarly and then measure relative size, and assuming that this was about 12 feet long. Infer about 7 foot of retreat of the edge of this. Back that way. From abrasion. Back this way, over 12 years, so about 7 inches a year, which is really comparable to local erosion rates in the Isla Vista area. So just keep that in mind, because when we go around the corner here and we come to Campus Point. Here's a big block of that light colored angular material. It's a remnant of maybe what might be called a sea stack if it was sitting out over here, surrounded by water at high tide. But here it is closer to the actual sea cliff, which is back here. And I want you to notice a few features here. There's a lot of tar up here. This is Santa Barbara Beach. But this material right here, that little remnant patch has a bunch of blocks that are eroding off it and landing on this relatively flat surface. I think this photo might be as early as maybe 52. I was doing some more research about Bob Norris. He was a geomorphologist at UC Santa Barbara, the first actually at UC Santa Barbara, one of the first anyway. This is that surface. This is that little chunk of rock. In about 1950. 2003, it looked like that. In the winter of 2003, it looked a little more like that. And today, there's nothing there where that used to be. So there's a big stack. This area has abraded away a little more. So it's something about these rocks are abrasion resistant. They're not wearing away from their sides too quickly. But the stuff on the top has eventually been excavated away. So my interpretation is that these relatively horizontal surfaces have nothing to do with abrasion platforms that slope from the sea cliff into deeper water. They're being cut at the level of that wetting line, and then they do surrender to abrasion eventually. Here is a picture from 2006 where I have some students and another professor with me, who's a graduate student at the time, Ted. Here's a very abrasion resistant knob of rock, and behind it, there's a bit of shale that's been protected. And 19 years later, that knob is worn down significantly. The sea cliff has retreated significantly, and that platform has retreated. Okay, now I'm sorry about not orienting the picture horizontally, but you can see if you look at the horizon here, that these surfaces very much kind of are more or less horizontal. So they're retreating more or less along that wetting line. Okay, now 30 years ago, I gave a graduate student talk in a seminar about this. I gave just basically a slideshow walk from Fish Point to campus, Fish Rock to Campus Point, and I pointed out some of the things that were obvious to see. And my advisor at the time insisted, no, this isn't uplifted by earthquakes. That's what it is. And even if you have evidence to the contrary, I can't dismiss that as not a feature. And what that ensued ultimately was trotting out the notion that these are evidence for maybe magnitude 7 earthquakes along the Santa Barbara coast. To amount to lifting it up out of the abrasion zone and getting it up to that level roughly 2 meters above the abrasion platform. And then sadly, some sort of systematic reduction of information in opposition. Which kind of made me a little angry when I discovered, and I only discovered it a few years ago when he passed away. But what I did also discover at the same time is he had a student working on the problem again. And I stumbled into the problem, and it wasn't something that he was interested in. But that student has evidence that of this retreat up here. That up about, he says, 0.8 meters above the toe of the sea cliff is where we get this attack level. That's actually looks like it's maybe more prevalent than the abrasion retreat. In which case it explains those ramps that we're getting retreat at the upper part of this cliff. In that light domain at a slightly faster rate than abrasion sort of catching up. So that could explain that whole ramp. His name's Paul Alessio, he's now working in San Diego County. So I'm sorry I didn't leave a lot of time for questions, but I want to invite questions now. This is not a problem that is solved. There's still work to be done to nail down all the details. The type of work that students, throughout the ages have been involved in. Designing an experiment to test one of these hypotheses. Such as the notion that Reyes said, well, what about that zone? Where else could you find, and could you find, algae growing at greater depths, or is it confined to the zone where they're happy? When you look at the intertidal zone, you'll find that creatures definitely have zones of happiness. In fact, that's how we sort of designate the supertidal, the buckshot barnacle, down into the mid tide, and then down into the lower tides. You get in the lowest of tides, you're getting maybe down to something like eelgrass that never wants to be high and dry. And won't survive if it is. So, questions? Any?
Thank you. Good talk.
Is there an estimate on the year that was lifted, or?
Well, no, as a matter of fact, there isn't. The notion that it's an uplift is also disproven, not disproven, it's unproven. It's an assertion right now. To get there, you'd have to string together a number of faults from Ventura, maybe all the way out to Point Conception. And to get enough fault length to get one event that would move up the ground that high. The fact that these things are still tied to the sea cliff is a little bit of a problem, however. In dismissing, the notion that they're cut in place. But I'll refer you to that same field trip guidebook that this article that I wrote is in on the Santa Barbara fold belt. With regards to what faults specifically might have to rupture. To get how long ago it might have occurred. We'd have to assume that it was, after human beings occupied the area that started keeping records. Right, of coastal things. And so it'd have to come before that, right? And it'd have to accumulate enough strain at the current rates of shortening to produce one event where the faults all accommodated uplift that would maybe even just say this was the peak. Like when a fault ruptures from one end to the other, it kind of unzips. And when you look at a fault and you look at the displacement on the fault, it's usually kind of angle, it kind of peters out towards the end. Sometimes there's peak displacement along it. So if this was the amount of uplift along the fault, it might have variations along it. That could just be like a unique place where they have the most uplift. So maybe I'm gonna go out on a limb here. the rates of uplift in coastal California are maybe about 1/4 of a millimeter, where we have active faults like the Palos Verdes fault, lifting up the whole Palos Verdes Peninsula. The sea cliff around here has been dated around 80,000 years. And, geez, I haven't done the math on this. It's a little hard to put it through in my head real quick. But 80 K, and we're talking about 0.25 millimeters or that's not right, 0.25. Yeah, that's right, millimeters per year. Per year,
Oof. 20,
is it about 20,000 years?
Mhm.
So it's taken 20,000 years to lift up that. If we did it in 2-meter increments. It'd get up at almost 40 meters. That's about 20 events. So about 1,000 years an event. That would be a ballpark estimate. Just a guess, yes.
2 questions. A, how did they, and I'm guessing, deal with the fact, as you said, it's still connected to the cliff face?
Oh, no, they ignore that.
They
They,
ignore that,
they
okay.
set up a straw man about
Okay.
these things somewhere else where it's hard to go look at them
Oh,
over on
okay.
the coast west of Gaviota. And refer to a 1951 paper by a guy named Upson who probably saw these benches, is my interpretation.
Okay, my,
I'd love to actually find the exact locations, right?
yeah,
Yes.
you mentioned that, the wetting zone seems to be higher, and the difference in the salt line.
Oh,
Is
at
there
that
any-
one-
At that one
At that
spot,
one stairway.
is there any, does anyone keeping track of wave height years and years?
I don't
Perhaps wave
know.
height's just increasing.
I don't know of that. I actually, no, that's not true. Recently, Alessio and Keller published an article back in 2020, I believe it was. There are some piezometers out in the water that
Oh,
are measuring the increase in pressure associated with rising tides, et cetera. I don't know how long that record is going on or whether they're still out there, but it's referred to in that Keller and Alessio
Oh.
paper. Anything else? Yes.
I have one quick question is, like as with the erosions, has the rising of the sea level and also change of the pH in the saltwater, like being calculated in terms of erosion?
Oh, well, as far as the rising sea level, it's tricky when you have a rising coast. And if your rising sea level is rising about the same rate as the coast, which is pretty much a lot of coastal California and Southern California where we have these folds and structures near the coast. Maybe the last 6,000 years, they've kind of been coupled in the same. It's rising about as fast, the sea level is rising about as fast as the land, so that should make for very extensive abrasion platforms under the water. So maybe 6,000 years of sea cliff retreat at more or less, a continuous abrasion platform forming in the offshore. It's getting buried with sediment. In the near shore, it's getting abraded and, retreating maybe with the sea cliff. Now, as far as pH and salinity and other things of water quality, I don't know, but I do know that land use above is definitely impacting the weathering of these rocks here. So, irrigation and other things. So all along that coast over where the stairs are, you can see roots of trees and other plants that are coming down and taking advantage of those fractures. And certain places where the salts are spreading out, where it's clear evidence that before the rock was excavated, there were paths that water was accumulating down, trickling down and evaporating and leaving salts behind. So there's definitely a human influence on those supplies of water, but I don't know of any studies that would link the wave, the ocean water to like a increase of salinity or anything that might influence. I don't know how well I answered the question, but just trying to see if I could think off the top of my head. Thank you very much for having me here. Appreciate it.
Thank you.